Direct memory access is a kind of a data transfer scheme in which the device is taking the control while transferring the data. We know that data transfer is possible uh, only through the certain set of lines. If certain set of lines are available, then only the data can be transferred. Suppose if we want to transfer the data from any peripheral or memory device to the processor, or from the processor to any one of the peripheral or memory device, the three important things which is required: one, the address of the source; second, the address of the destination; third, the actual data which has to be transferred; and the fourth one is the control lines to do the data transfer work. And all these lines, this data bus, address bus, and the control bus, all these buses are under the control of the processor. So, if we have to transfer a data from the peripheral to the memory, or from memory to the peripheral, or from one memory to another memory, then the normal process which is being adopted is first to copy the data from the source to the processor, and then from the processor to the destination. Now, the source and destination may be the memory, or maybe the peripheral, or maybe one may be peripheral and then may be memory. So, it is going to waste too much time, because unnecessarily the data is being transferred from the source to the processor, and then from processor it is being transferred to the destination place. So, that is why another data transfer scheme has been proposed with the name that direct memory access data transfer scheme, which is commonly used for high speed data transfer and the data transfer in between the two peripherals, including the memory. So, this particular is possible with the help of two signals, which is available with 8085, that is called hold signal and HLDA signal. The working of the hold signal is, if any device wants to request the processor that he want to take the control of the address bus, data bus, and the control bus, then it requests by sending a high signal to the hold input of the 8085, and processor, once completes its current instruction execution, it acknowledges that by sending the hold acknowledge signal. So, this process is possible, means direct memory access data transfer is possible only when the control over these buses is taken out from the processor part to the device part. So, for that particular purpose we use a controller, and that is known as DMA controller. The purpose of using the controller is to manage the data transfer in between the different memory or the peripheral device under its control. Thus, it is going to bypass the microprocessor unit. So, as I told you that it uses two signals. So, hold signal is an active high input signal of 8085, and after receiving the hold request, the microprocessor releases the buses to take the control by the controller itself, and acknowledges by sending the hold acknowledge signal. So, it means this DMA controller will be using these signals for providing the facility of transferring of the data in between the two devices. So, whenever it is taking the control of all the things, it will be working as a processor. So, that is why normally the DMA controller is said to be working in two different mode. One is the slave mode, another is the master mode. It will be working as a slave mode whenever it is requesting the microprocessor to release the buses and to take the control over the buses. And once the control of the buses are released and given to the charge to the controller, controller starts working as a master. So it means the DMA controller must have the capability to handle the data bus, to handle the address bus, as well as to handle the control bus. So as I told you that it works in a slave mode as in the master mode. One time it is working as a slave mode, another time it is working as a master mode. Now let us come directly to the 8237 DMA controller. It is an integrated chip of having 40 pins, and this DMA controller has 4 independent channels which are capable to transfer 64 kilobytes of the data at a time. Now it means that it must interface with 2 kinds of devices, one with the microprocessor, another with the peripheral or the memory. So whenever the input whenever the processor starts, whenever this DMA controller starts its works, first of all it serves as an input output device for the microprocessor by sending a request signal, and at that time it is working in a slave mode. And another time whenever it is the control of the buses is given by the processor to the controller, it starts working as a in the master mode, and at that time it is also called as a data transfer processor. Now it has many control signals which are used for the controlling purpose, for the communication purpose, as well as the different segments in which the DMA controller can be defined is the DMA channel and the interfacing, DMA signals, system interface, and the DMA execution. So this is the block diagram of 8237 DMA controller, in which you can see the there are address lines. As we know that there are 8 address lines physically available in 8085. So these addresses lines are connected to the 8237 controller by connecting these A0 to A7 lines of the 8037. Besides that, it has many memory registers, address registers, count registers, and there are certain signals which is available on the control signals which are available on the right side of the block diagram as well as to the left side of the block diagram. So we will discuss in detail about all these signals. First of all, let us discuss about the DMA channels and its interfacing. Now as far as the 8237 is concerned, it has 4 independent channels, and in channel number 0, channel 1, channel 2, and channel 3, and internally all these channel has 2 registers associated with that. One is used for loading the starting address of the byte to be copied, and second is used to load the count value, that how many number of bytes has to be transferred. So that is why, since we have 4 channels and individual channel having 2 registers, so total number of the registers are 8 registers. So let us see, there is channel 0 having memory address register and the count register, channel 1 memory address register and the count register, channel 2. Similarly, we have 4 channels, so there are 8 register. Each channel will have memory address register as well as the count register. The purpose I have already explained. Now the address of these registers are determined by how it will work. The address of these registers are determined by the 4 address lines from A3 to A0, as well as the chip select signal, because until this chip is not selected, it will not work. So this address 000 on the line A3 to A0 is going to give you the address of CH0, that is channel number 0. Now, the address of the individual register of each channel is also different, meaning thereby the memory address register will have address 00 and the channel count register, channel 0 count register will have the address 01. So, it all depends upon A0, a value of A0, A1, A2, A3 and chip select, and chip select is connected with the output of the 3 to 8 decoder where the input lines are A4 to A7. So, let me give you the example of that how it is being done. Now, the address as I told you is determined by the A0 to A3. So that it will be different value of A0 to A3 is going to select the individual registers. So, the last we have total 16 registers, out of that 8 registers belongs to the 4 different channels. Now, A7 to A4 is the chip select one and A3 to A0 is the register select. Now, as you see in this figure, since the chip select signal is connected to O0, it means the value of A4, A5, A6 and A7 will always remain 0 for selecting the particular chip, and it is the value A0, A1, A2 and A3 that will determine the address of the individual register. So, that is why A4 to A7 is 0 and A3 to A0 is, once it is 0, it is selecting it is giving the address 00 for the channel 0 MAR, and for 00001 it will be giving 01, that is channel 1 count register. Similarly, when the value of A0 to A3 will come 111, so it will give the address 0F for the mask register. Now, besides these 8 registers, there are 8 more registers available in the 8237. These registers are status command registers, request register, single mask register, mode register, clear byte pointer, master clear and then all mask bit. So, there are 8 more registers used for different purposes, and all these registers have their individual addresses depending upon the binary pattern of A0 to A3. Now, let us now discuss the DMA signals. Now, these DMA signals are grouped into 2. One are those signals which are available on the right side of the DMA, and another is set of signals which are available on the left side. So, we will discuss individually. So, first of all, we will discuss the right side signal. What is the right side signal? We see in the right side we have 8 signals: DREQ0, DREQ1, DREQ2, DREQ3 and similarly DAC0. So, DREQ stands for request and DAC is the acknowledgement signal. So, since we are using 4 channels, so for individual 4 channel 4 request signal and individually acknowledgement is concerned, the channel will be acknowledging by giving the DAC signal. So, that is why request signal is input to the 8237 and DAC signal is output to the 8237. So, DREQ0 to DREQ3 is a DMA request and DAC0 to DAC3 is a DMA acknowledgement. So, that is all about the right hand side signals. Now, come to the left hand side. Left hand side we have signal AEN and ASTB. AEN stands for address enable and ASTB stands for address strobe active. Now, this high output signal, this address is, both the signals are high output signal, and it is used to latch the higher order address bytes to generate the 16-bit address. Now, you can see the position of these two signals. This is AEN signal and there is ADSTB. Both the signals are high output signals, and the purpose of these signals is to load the 16-bit address on the higher order, to latch the higher order bytes to generate the 16-bit address. Now, we have 2 more signals, MEMR and MEMW. Let us see where it is, MEMR and MEMW. So, if the input peripheral devices are working in a input output mapped input output mode, then these two signals are connected with the IOR and the IOW. But if the input output devices is working in a memory mapped input output, then MER and MEW is connected to the MER signal and MEMW signal to the microprocessor. Now, as far as the addresses are concerned, A3 to A0 and A7 to A4, these are the bidirectional address lines. A3 to A0 is a bidirectional address lines which are used as an input to access the control. It is used to input to access the control register, and during the DMA cycle these lines are used to output as the output line to generate the lower order address bus, and which is combined with the A7 to A4. Now, if you see A4 to A0 to A3, this is bidirectional. Bidirectional line means once it is used to select the individual registers used in the 8237, and another time it is used to send. That is why these signals are bidirectional signals in case of 8237. Now, the HRQ and the HLDA signal, which is available also in this hold signal. HRQ is the hold request and HLDA is the hold acknowledge signal. Now, this is the HRQ through which this line is connected. HRQ line is connected to the hold line of the 8085, and hold acknowledge is connected to the hold acknowledge of the 8237. The purpose is same. If the 8237 wants to interrupt, it will send a high signal to from the HRQ through HRQ to the hold of the 8085, and it receives the HLDA signal from the 8085. Besides this, there are more signals. Ready signal, you know the purpose of ready signal, reset to reset, and the clock to provide the synchronization of 8237 with the 8085. Now, as far as system interface is concerned, when a transfer starts, when the transfer begins, DMA places first of all the direct memory access control places the lower order bytes on the address bus and higher order bytes on the data bus, and it is possible only when it asserts AEN and ADSTV strobe signal, address enable and the address strobe signal, through which the higher order bytes are placed on the data bus. Now, these two signals are used to latch the higher order bytes from the data bus. So, that is why it is going to place the 16-bit address on the system bus. And after the transfer of the first byte, the latch is going to be updated. Now, let us go to the interfacing DMA controller interfacing with 8085. The circuit, the block diagram is given here. Now, in this block diagram you will see there are two latches which are being used. 373, one is latch number 1 and another is, this is latch number 1 and another is latch number 2 to receive the addresses on the address bus as well as on the data bus. And the rest of the 8237 configuration remains same. The database is connected with the data bus of the 8237 and so on. Now, how DMA execution take place? As I told you that it works in two fashion. It is first working as in a slave mode, and another time it is working as in a master mode. Now, one more whenever it is working as a slave mode, in that particular mode, whenever DMA controller starts its operation, and at that time it is working as a simple input output device, and microprocessor is going to select this DMA through the chip select signal, and it is going to write something on the control word in the channel register or the command status register, and at that time it is using simple control signal, that is IOR, IOW. So, meaning thereby it is working in a slave mode whenever DMA starts its work, and whenever it receives any kind of the information from the any peripheral or the memory device that it wants to transfer the data through direct memory access data transfer scheme. So, at that time the DMA controller will be sending the signals to the microprocessor, and at that time until it receives the acknowledge signal, it is working in a slave mode. Why it is called slave mode? Because at that particular time it is not in the full control of all the buses and it is in the request mode. So, second one is the master mode. In this master mode, the operation of 8237 starts, in which it is working as a data transfer processor. So, in this master mode, peripheral sends the request signal. The request signal is received by the 8237 and the channel is enabled by using the control logic, that is by sending the high hold request signal. So, what happens in the next cycle, the hold acknowledge is received by the 8237 and at that particular time DMA is going to assert high AEN and enable latch 1. At that time it is going to make the AEN signal high, and that is with the help of that it is going to enable the latch 1. As I show you that there are two latches which is being used. And then after that it asserts ADSTB high, it uses second signal and places the content of the data bus, which is higher order byte of the starting address, on the A15 to A8, and at the same time DMA also outputs the lower address on the A7 and A0, that is as a lower order address bus. So, when the entire address is now available, the address bus on the address bus, DMA sends the DAC signal to the peripheral. So, DAC means once the addresses are available on the address bus. So, what happens, since the device who has requested the 8237 to start functioning, when it makes the address available on the address bus, then it sends the acknowledge signal to the peripheral and says it to start the operation. Now, the DMA control continues, this data transfer operation starts now, and this is going to continue, the data transfer operation is going to continue by asserting the necessary signals which are required. If it is input output operation, then it will be asserting IOR or IOW. If it is memory operation, then it will be asserting MER or MEW, because at a time it is working only as a one of the signal will be activated. And this process is going on till the DAC signal remains high. Once all the data is being transferred from the source to the destination, the DAC signal goes low. So, whenever it is the end of the data transfer, DMA asserts at end of the operation signal low, and that can be used to inform the peripheral that the data transfer is complete. And how it came to know? We know that we have used two registers for the individual channel, and any channel can be used to transfer 64 kilobyte of the data, and every channel has two registers. One is the starting address register, and second one is the count register. So, once the 1 byte is transferred, the count is going to be decremented, and till this process is going on, the counter is going to be decremented till it becomes 0. And once it becomes 0, it gives the information in the form of an end of the operation, and then only it informs the peripheral that all the data transfer is done and it is complete. So, that is all about the 8237